So chapters 8 through 10, or topics 8 through 10, are the ones that will be covered on the exam. 11 has been pushed back to the final, so don't worry about fluid stuff for this exam. But in topic 8, that's rotational kinematics, so the properties of rotational motion. And so as far as what to know here, I guess I'll just give a quick review and then say what the most important things are. So rotational motion, we can talk about very analogously to linear or translational motion. And so instead of using a regular displacement, meaning the change in position, we talk about the change in angle relative to some reference. That's the angular displacement. And we can talk about the rate of change of that displacement. And that is a rate of change of the angular position, which is the angular displacement over the time interval. That gives you the angular velocity. In the limiting case of a very short time interval, that average angular velocity is the instantaneous angular velocity, and that's what becomes relevant in the rotational kinematic equations. And then same with angular acceleration, it's the rate of change of the angular velocity. So really the first thing to hone in on is being able to apply the rotational kinematic equations. So I think all of page 87 is a good thing to be familiar with. Basically, when you're reading a problem, be able to extract that something is a angular velocity versus an angular displacement or angular acceleration. Usually it will either say that or the units should tell you which one is relevant. And then just pick the right kinematic equation to solve for what you're looking for in terms of what else you're given. And the other piece is just knowing directions here. So remember that anything counterclockwise is considered positive rotational motion. So it's a little bit backwards to what you might think initially, but it's just the convention used. So counterclockwise motion is considered positive angular motion or rotational motion. And so if you're given that something is rotating with a positive angular velocity, then it is rotating counterclockwise. Wait, have I been saying clockwise this whole time? Counterclockwise is positive, whatever I said before, but counterclockwise is positive. And so if you have an angular velocity that is positive, then that thing is rotating counterclockwise. And so the other side of that, the question is, if you have an angular acceleration that's negative, what does that tell you? That one's not rhetorical.
Is it going to be slower?
Is it what?
Is it going to be slower?
So yes, because the angular velocity in that case is counterclockwise, a negative angular acceleration means a clockwise angular acceleration, which is opposite the direction of the angular velocity. So just like with linear motion, it's important to know that regardless of the directions of things, it's the direction between the angular velocity and angular acceleration that tells you whether something's speeding up or slowing down, so rotating faster or slower over time. So what if both the angular velocity and the angular acceleration were negative? The angular velocity is negative. What does that tell you about the motion of the rotating object?
It's moving counterclockwise. Oh, it's moving clockwise.
Clockwise. Okay. So then if the angular acceleration is also negative, what does that say?
It's speeding negative direction?
Yes, so it's rotating faster clockwise, right? So the fact that the angular acceleration is negative doesn't necessarily mean that it's always slowing down. It's the fact that it's in the same direction as the angular velocity in this case that means it's speeding up. But previously, when I said the angular velocity was positive, so counterclockwise, a negative angular acceleration would be in the opposite direction. And so that's what tells us that it slows down in its counterclockwise rotation. So the relative directions of the velocity and acceleration are what matter as far as speeding up or slowing down, just like with linear motion. Okay, so knowing that distinction is a good thing to know. And then there's just a couple rotational kinematics problems. So be able to apply those kinematic equations. There is a little bit on relating angular and tangential variables. So remember that the relationship between pretty much every tangential variable and angular variable is just the radius, r. That's what determines if you're given, say, an angular speed, that can give you the tangential speed. So that's what this equation says, is that if you've got something like a fan rotating at an angular speed omega, points farther from the axis of rotation, so greater radius r, have to be moving faster tangentially to their circular paths because they're covering more distance in that same amount of time. So a point on the outermost part of the blade of this fan has to be moving faster, covering more distance in the same amount of time than a point closer to the center, because the outer one is moving on a larger circle than the inner one. Even though they both have the same angular velocity, they're moving through the same angle in the same time. One just has to cover more distance in that time to do that. So in general, just how do the angular variables relate to the tangential variables? So that first equation, and then this one right here, tangential acceleration is r times the angular acceleration. And so again, to get a good physical sense of what each of those mean, this is a good example to look at, and that drawing tells you that as the helicopter blade rotates through a certain angle, if we're saying it has some angular acceleration, it was rotating at some rate initially, but then as it continues rotating, it's rotating faster over here. That also means that a point on the blade that was moving at some tangential speed initially is moving at a greater tangential speed after. And you can relate the tangential acceleration that caused that tangential speed to change to the angular acceleration that caused the angular speed to change. I'll be honest and say there's not a whole lot of calculating the total acceleration of something on the exam. So you've already been tested on centripetal acceleration, so I'm not going to double down on that. And so while it is good to know that a centripetal acceleration is not the only possible type of acceleration that can happen during circular motion, because if you have something speeding up as it moves around a circle, it also has a tangential acceleration, and the total acceleration is the vector sum of those. That's not emphasized on the exam. Rolling motion is also not heavily emphasized because I think that is a little bit more complicated, and it's really just connecting linear motion to rotational motion. And so I think the homework did well enough covering that bit. It will not be on the exam. Okay, so that's topic 8. Are there any questions on that before I move into rotational dynamics?
Well, I have a question, but it's not on the notes. It's about the practice exam.
Okay, so I think like last time, I'm gonna wait till we get through the whole little review, and then we'll just do as many practice problems as y'all want to do.
Oh, okay. Thank you.
Okay, so any other questions about just clarifying things on these notes? Because yeah, we'll do plenty of practice problems after I run through this. Okay. So rotational dynamics, torque is the first thing we talk about. That is what causes or changes the rate of rotation of something. So if you have something rotating at a certain angular speed, the only thing that can cause that speed to change, at least if we're not talking about conservation of angular momentum, is torque. So you have to have a force acting at some distance from the axis of rotation, meaning through some lever arm. And so torque depends on both the applied force and the line of action through which it acts. So I think that can be a difficult concept, the line of action. So I am going to jump off to the side here, if it will let me, into this whiteboard, which I guess closed down. So we'll open that back up. So let's say we've got and like before, I will send out whatever stuff I fill out on the whiteboard as a PDF at the end. So this is a top-down view of a door. You've got a hinge right there. And everyone's seeing this whiteboard, right? Yes, no, maybe, yes,
Yeah.
okay. All right, so we've got a doorknob over here. Let's say you apply a force, and make that a little straighter. Apply a force like that. How can we find the torque that that force produces about that hinge? I guess what I'm asking is, what is the lever arm for this force?
So it's the perpendicular line from the axis.
Yes, so I want to make sure that it's clear what that means. So to me, the easiest way to determine it is you just draw a really long line, the line of action of this force. So the line of action is just a force acts in a particular direction. So if we draw a line in that direction, that is the line of action of that force. Now we look at our axis of rotation, which is the hinge. The lever arm is the line that we can draw from the hinge to this line of action that is perpendicular to the line of action. So I'm going to draw 3 different lines here, because I think seeing what isn't a lever arm may help you with seeing what is. Of these 3, call them A, B, and C, which is the lever arm for that force?
B.
Okay, what do others think? Asia, Catherine, Kala, what do you think?
I thought B also.
Okay. All right, maybe one more, Catherine or Caller. What do you think? Okay, maybe they are away at the moment. Yes, it is B. And that is because that is the only line we can draw from the axis, which is the hinge, to the line of action of this force that is perpendicular to it. The others make angles that are not 90 degrees with that line. So no matter how complicated the diagram may look, that's all that matters. So if you have, let's see, doors are the easiest thing to draw here. So I'm just going to do another door. So if you applied a force like that, do the same thing. Draw your line of action. It's just the line that that force lies on. You can make it as long as you want in both directions. How can I find the lever arm here?
It will be the y-axis.
Yeah, so it's the vertical line. I could, maybe I get it wrong the first time. I'm like, well, maybe it's that. That seems right because it's perpendicular to the door, but it's not perpendicular to the line of action of the force. The only line that is that one going straight down. So that is my lever arm in that case. From there, it's just what angles are you given, do some trig, and that will give you the length of that lever arm. But I think the hardest part there is just determining or drawing the right lever arm. Okay, so a little bit of a tangent aside, but I hope for anyone who that wasn't clear before, that cleared things up. So that's exactly what this example has, the Achilles tendon one. You recognize the line of action of the force, the axis of rotation is the ankle joint in this case. There's only one line you can draw from the axis of rotation to the line of action of the force that's perpendicular to it. And so that is our lever arm. And then, like I said, from there, finding the length of it is usually just a bit of trig. So on this exam, there is some stuff about calculating torques. But in the context usually of something involving the center of gravity. So I'll come back to this equilibrium part in a second, but what is the center of gravity?
When the object is balanced?
So if you support something from the center of gravity, it will balance because the center of gravity is the point through which, yes, takes here. So the center of gravity is where you can treat the weight of an object as acting when you're calculating the torque that weight produces around an axis. But if your axis is the center of gravity, that's where you're supporting this thing, like the hand here, then that force, that weight of the object acts through the axis of rotation and so produces no torque. That's what balancing an object is, at least if only its weight is acting as a force there. So yes, Kala, in that if you support the object at its center of gravity, it will balance. But in general, the center of gravity is the point we can treat the weight of an object as acting in calculating the torque that object produces around an axis. So if you're told that something is uniform, what does that tell you about where its center of gravity is?
Is it in the middle of the object?
Yes. So that's because for a uniform object, you've got as much weight on, say, one side of that center, that geometric center, as on the other. And so you add up all those little bits of weight and the torques they produce, you end up having just as much torque on one side as the other. And so you can treat it as if all of that weight is acting through the center of gravity. So uniform means that the center of gravity, and therefore where you're calculating the torque is acting through, is the middle of the object. Okay. So there is one where you'll be told that you have a uniform something, you want to find the torque it causes around an axis. Just remember, it's at the center of the object. Okay, back to equilibrium. So what is mechanical equilibrium in its fullest sense? Because in chapter 4, we gave one definition, but we realized here that we need a little bit more to fully define it.
Is the sum of the forces that acts in the y and the x-axis 0, and the torque, it's also 0?
Yep, so the torque is the new thing here. There should be no translational acceleration, which is what we saw in chapter 4, but also no angular acceleration. It should not be rotating any faster or slower. It should stay rotating at the same rate, or if it's not rotating, it's at rest. At least it's just not rotating. So in this example, with the dumbbell, we were able to find different things about this system by applying those equilibrium conditions, both that the net force is 0 and the net torque is 0. There's nothing even remotely as complicated as this on the exam, but it is good to remember that if something is balanced, then the net torque on it has to be 0 and the net force has to be 0 on that object. So we'll say, again, this is just a good page to be familiar with the concept of, as is the definition of center of gravity in that uniform piece. So center of gravity is the point at which an object's weight can be considered to act when we're calculating the torque that that weight produces. And if, again, that point happens to be also the axis of rotation, the center of gravity is, then the object will balance, because then it's not producing any torque around the axis. Okay, I don't ever ask you to explicitly calculate the center of gravity. So this, the example where we calculated that for the arm, there won't be anything quite like that. Okay, second law for rotational motion. So this is the analog of Newton's second law for translational motion, which says that the more net force you have acting on something, the more that thing will tend to accelerate, but the more mass that thing has, the less it will tend to accelerate. For rotational motion, the more net torque you have acting on something, the more it will tend to angularly accelerate, meaning rotate faster or slower. But the more moment of inertia you have, the less the thing will tend to angularly accelerate. So you have a lot of moment of inertia. That means it's hard to get the thing rotating. It's also hard to stop it rotating. What's important is that it makes it hard to change the state of that object's rotation. So I also don't really ask you to calculate any moments of inertia. It's just being able to apply that idea of the more moment of inertia something has, the harder it is to get it rotating, and the harder it is to stop it from rotating. And so things like these equations for the moments of inertia, if they're needed, they will be given. That's a good example right there. And that is one we did in class. We proved that what we said here is what happens in real life. Okay, so just keep that in mind that the more rotational inertia or moment of inertia, same thing, that something has, the harder it is to get it rotating. And so it's not as easy to get rolling down a ramp. Things with more rotational inertia lose the race down the ramp. Angular momentum, there's a tiny bit on that. So it's just that if angular momentum is conserved, which happens when you don't have a external net torque acting on a system, then you can apply this equation here, which says that the angular momentum, which is the product of moment of inertia and angular speed, really angular velocity, but direction gets a little bit weird for angular variables, so we didn't go into that. It says that if you have a system where no external net torque is acting and you reduce the angular moment of inertia of that system, then its angular speed has to increase. So the prototypical example of that is the ice skater. When she brings her arms in, does she increase or decrease her moment of inertia?
Decrease?
Decrease, because she is concentrating her mass closer towards the axis of rotation. The biggest factor in moment of inertia is how far the mass sits relative to the axis of rotation. If you have a lot more mass farther away from the axis, the thing has a lot of rotational inertia or moment of inertia. And so when she brings her arms in, she's reduced her moment of inertia. What does that say about her angular speed? How fast she rotates?
It increases.
It increases, because if we have the moment of inertia go down, then to keep the product of moment of inertia and angular speed the same, that has to go up to compensate. Okay. There's nothing really with point masses, which is what this is. It's applying the same idea of conservation of angular momentum, but where specifically the moment of inertia is that of a point mass, that mr squared. So I think this example, the conceptual example, is a better one for this exam than this point mass one. Okay, that concludes that chapter, and then we move into the last one on the exam. So any questions on 9 before moving into 10?
You said the last example is not going to be on the exam.
Yeah, so this example with the Earth and calculating its tangential speed at apogee and perigee, there won't be anything like that. There will be things more like this one, where you're just told that the moment of inertia changes by some amount. As a result, how much does the rotational speed change or angular speed change? Okay. That's 9. And then 10. In a sense, 10 is pretty short because I cut half the chapter. Maybe not half. I cut the last 2-ish sections on Young's modulus and elasticity and stuff. So the main things are up through the page on the pendulum. There's not anything on damped harmonic motion or driven harmonic motion. Those are just things that I think are much more interesting in physics, but it was just introduced at a conceptual level down here, so I can't really ask too many questions on that. So up through 103 with the pendulum is where questions kind of come from. So the idea is for a spring that the restoring force that spring exerts on an object as the spring is compressed is proportional to how much that spring is displaced from its equilibrium position, which is where it is not strained at all by anything. It is just sitting there, not stretched or compressed. However much it gets stretched or compressed relative to that position determines the amount of force it exerts back to try and bring itself back to equilibrium. So that's what Hooke's law says, is that the force the spring exerts is opposite to the negative, the displacement of the spring from equilibrium, and proportional to it by the spring constant K. So the stiffer the spring, the larger the spring constant. That means the spring is pulling back harder for a given displacement if it's stiffer. And then simple harmonic motion occurs when you have a restoring force proportional to that displacement, which is exactly the case for springs because of Hooke's law. And so for simple harmonic motion, that just means the thing oscillates back and forth sinusoidally, meaning if you graph its displacement versus time, you get a sine or a cosine. So at this point, I think the important things are knowing this relationship, Hooke's law. So the force that the spring exerts as a result of being displaced from equilibrium is negative kx. And there is a problem where it would help you to draw a free body diagram, but I guess it's not strictly required. But just knowing that relationship between the displacement of a spring and the force it exerts. Then for simple harmonic motion, there's not a lot on this reference circle stuff. That was just a means to an end. That was to get that the displacement over time of a simple harmonic oscillator is given by this equation. And then it let us find also the velocity and its maximum value and the acceleration and its maximum value. So those end equations we got are relevant. The reference circle thing that we use to get those equations is not, as far as something to be tested on. It's just how we ended up finding those equations. But this example right here is a good one, both conceptually and for some calculation-based stuff that's on the exam. So with the speaker, knowing where the velocity is maximum and 0, as well as where the acceleration is maximum and 0. And then we found this equation for the angular frequency of a mass spring system. That is good to know how it depends on the spring constant, the stiffness of the spring, and then the mass that's attached to it. So how could we get for a certain system a higher angular frequency for its oscillations back and forth? There's two things we could do.
Is it to use the equation A omega?
So not the A omega, because what does that equation tell us?
It gives the max speed.
That gives us a speed. So speed is the distance it's covering per time, the rate at which it's moving. Frequency is related, but it's about how many cycles the spring is moving through in a certain amount of time. So what I mean by that is, say the spring is stretched all the way out, you let it go, it compresses, comes back, compresses, comes back, compresses, comes back. How many times does it do that in a certain amount of time? That's what frequency is. So that's what F is, but then angular frequency is just relating that to how many times the corresponding point goes around the reference circle. So it's just another way of describing that motion. What ends up being more physically important is this F instead of omega, but omega is easier to calculate. So anyway, I'm asking, how can we change omega or F?
You asked how can we change F? Like such as the frequency?
Yeah, so frequency depends on stiffness and mass, right? Or the spring constant and mass. So what could we change in this picture to get a higher frequency? Meaning it's going to complete more of those cycles per second.
The mass?
Yep, so mass is one thing you can change. What should you do to the mass to make it oscillate faster?
Increasing the mass or decrease it?
So the equation tells us if we increase the mass, we're dividing by mass, so we're going to get a smaller angular frequency. So yeah, if we decrease it, we will increase the angular frequency. In terms of the physics, that should make sense because it's not having to drag along as much mass. The spring is not. And so there's not as much inertia, making it difficult to be able to compress and then stretch the spring back out. So the less mass you have, the more frequently that spring can oscillate back and forth. Okay. What's the other factor in frequency that we can change in order to get a higher frequency?
Is it the displacement?
So not displacement. What does
This-
this depend on?
The spring constant?
Spring constant. And what does that tell us about the spring?
How stiff or how like,
Stiffness.
Yeah,
Yeah.
so how stiff it is. If we used a stiffer spring, one that as you try and compress it, it pushes back harder than another spring. That also makes it so that the mass spring system will oscillate back and forth at a faster rate, have a greater frequency. And so same deal there of if you've got something very stiff, very responsive to that push, it's going to push back more when it's compressed than one that is less stiff. So if that doesn't make sense, you can always fall back on the equation that says if K is larger, omega is larger. If M is larger, omega is smaller. But physically, it has to do with if you have less, you have to move back and forth. It's easier to move back and forth. If you have something that is pushing and pulling harder as the thing moves back and forth, it is also easier for that system to move back and forth. Okay, so that equation is important, but only as far as interpreting what it means, right? I don't want you to come away from physics thinking it is just a list of equations that you have to memorize. They're just a way of summing up what should make sense about the system that we're looking at. So for this one, it should make sense that the less mass you have, the easier it is to kind of pull it back and forth and so oscillate. The stiffer the spring you have, the harder it's pushing and pulling. That also makes it so it's easier or it oscillates more frequently. But this equation sums all that up in a nice convenient package. Okay, so knowing that expression for the frequency, and then it's sort of conceptual implications. There are a couple conceptual questions on simple harmonic motion. And let's see, energy. I tried to give the easiest possible energy problem that still covers it, because these can get a little bit difficult when you have both, for instance, with this one down here, both gravitational potential energy and elastic potential energy changing because the thing is falling while the spring is also stretching. So I don't have any of that involved. I just have one where it's kinetic energy and elastic potential energy involved, and how when those are conserved, you can find out some information about the motion of something as a result. So for that, I think this example is better than the second one. If you can make this example make sense, then you should be fine on any energy related stuff on the exam. And last is the pendulum. There's only things on simple pendulums, meaning the ones where the moment of inertia, we just say we've got a little point mass hanging at the end of this string. And so we can simplify this equation for the angular frequency that has the moment of inertia in it down to this much simpler one. That's the square root of g, the acceleration due to gravity, over the length of string that the pendulum is hanging from. So in terms of applying that, this example pretty much covers your bases. Now, again, with all of these, I'm not saying these examples are the only thing you should study, but they do cover what you need to know about that type of problem. So I've asked a couple people what helped them most when they did do well on exams, and it seems like the practice, if you go back and look at those, so each chapter, there was the practice chapter 8, practice chapter 9. Those questions helped them a lot. And then, of course, there is the practice exam, which we'll get to in just a minute here. So those would be my main recommendations. And then just these specific examples, I think, should help as well. But practice for the concepts, especially. Okay, so that's the cutoff for 10. And so that's the cutoff for the exam. Are there any questions at this point before jumping over to the practice exam?
Can you please do a question that we have to use the free body diagram?
Okay. So let's see if one of these has something like that. So I guess none of these are strictly like that, but this one had a ball hung from a vertical spring oscillating in simple harmonic motion. What's the maximum acceleration of the ball? So I'm not going to solve this problem yet. We can do that in a second, but just going to say that if we wanted to draw a free body diagram for this ball hung from this vertical spring, so it's saying we've got something like that, and a ball hung at the end. How would we draw our free body diagram for that ball when this spring is just hanging there? So the ball's hanging at the end, it's not oscillating. It's just pulled the spring down a little bit, stretched it out a little bit as a result of the ball's weight. And then it reaches an equilibrium state where they're both just sitting there at rest. What does the free body diagram for that look like?
So the weight component will be downward, and the force from the spring will be upward.
Yep. So you've got weight acting downward. That's mass times the acceleration due to gravity. And the spring force acting upward. I'll just write it, I'll write a spring equals negative kx. So I will say we've already accounted for the direction here. So we got to be careful when we're doing the net force acting on this thing. So net force in the y direction is, what would it be?
mg and F spring.
Yeah, so we've got that since the spring was pulled down, its restoring force acts up. So we would write it as kx because the negative part of that, the direction just says that that force acts back upwards, opposite the direction of the displacement. So in terms of the components, it's positive kx because it acts upwards, minus mg because that acts downward, right? That's our negative y. That's our positive y. And so if it's just at rest, then it has to be the case that kx equals mg. And that actually tells you exactly how far the spring stretches as a result of hanging this mass. It's mg over k. Okay, so that's the kind of thing I mean when talking about a free body diagram that might be involved, is that's about as involved as one gets.
Okay, on the exam, not on the exam, on the homework, there were a question that we had to draw the free body diagram, and there were two forces, Fx and Fn.
Fx and F what?
Fn, F sub x and F sub n.
Oh, so you might have like a ball stretched out, but sitting on a table. So what's acting on the ball is, in this case, you've got, oh, but when they say Fx, they're talking about the force applied to the spring, not the force the spring applies. So in that case, we'd be talking about one like you're applying a force to compress the spring by a certain amount. Ax, and it's sitting on a table, so we've got a normal force and then a weight of this object. And if there's friction, that also factors in here. But the Fn is just because there's something supporting the object, or it's being pressed up against a wall or something, so that thing is exerting a normal force back.
What about the friction?
So you're compressing the spring to the right. So the ball is moving to the right, the relative motion between it and the floor is to the right, so friction acts back to the left. Kinetic friction, since it's sliding across. So if friction is involved, as always, friction just acts in the direction that opposes the relative motion between the two objects that it's occurring between.
And you said to the best material to study for the concept is the practice, right?
Yes, the practices for each topic, and then for calculations, probably the practice exam is your best bet. But as always, I think the reference sections are good if you just skip the unit conversion part by just Googling the unit conversion. Okay, so are there specific practice problems we want to go over?
Number 5. I mean, I had just took a guess at it and got it right, but I'm not sure exactly how to go about getting it.
Okay, so fan rotating with an initial angular velocity of 1,000 revolutions per minute. In 2 seconds, the angular velocity decreases to 200 revolutions per minute. Assuming the angular acceleration is constant, how many revolutions does the blade undergo during this time? So first thing I would do is to label what I'm given here. So omega naught, it's initial angular velocity. 2 seconds is the time. The final angular velocity is 200. And then what does this part tell us? Assuming the angular acceleration is constant.
That's not changing.
That is not changing, but what does that mean applies here?
Using the kinematic equations.
Yes. So although we've always assumed, and we're assuming here, that the angular acceleration is constant, and in problems where we're talking about linear motion that the regular old acceleration is constant, that is required to be able to apply the kinematic equations. They rely on the fact that the acceleration is taken to be constant. So when you see a line like this, it's not necessarily telling you anything for solving the problem other than the fact that, hey, you should probably use the kinematic equations. How many revolutions does it undergo? That's talking about an angle moved through. So that's our angular displacement. And so we want to know how to find theta given omega naught, omega, and t. So is there an equation that relates all those things?
The 1/2 times omega naught and then omega final times time.
Yep. So this is just one of the kinematic equations. You can look in your chart and this is what you'll see. So the only hiccup here is that our initial angular velocity is in revolutions per minute, final is in revolutions per minute. This is in revolutions, but time is in seconds. So we have a choice here. We could either convert this, the initial angular velocity, to revolutions per second, and also this to revolutions per second, or we could just convert this time to minutes, okay? Because we need consistent units to be able to get out just revolutions. If we had revolutions per minute multiplied by seconds, we'd have units of revolutions times seconds per minute, which is not just revolutions. So just for the sake of it's less work, you know, I'd say convert the time, because then that's only one conversion compared to converting both angular velocities. So I'll do it separately and then we'll just put everything into this equation. But the time is 2 seconds, but we want it in minutes. So we need to get minutes out, but get rid of seconds. How many seconds are in a minute?
60.
Yep. So 1 minute for every 60 seconds. Seconds cancel. We're left with units of minutes. So it's 1/30th of a minute, whatever that is as a decimal.
0.03.
0.03 seconds. Okay. So now we have consistent units because we put everything in. Omega naught is 1,000 revolutions per minute, plus omega is 200 revolutions per minute, times, should not have had seconds there. That is 0.03 minutes because we converted to minutes, times 0.03 minutes. And so if this had been in seconds before, then it wouldn't cancel the minutes over here like it does now. And so we're left with, after that canceling, just units of revolutions, which is what we wanted. So we run through this, do the math. What number do we get? 1/2 times 1,200.
18. So B 20.
Okay, that seems good to me. It's probably because of rounding off this 0.0, the 1/30th to point.
Hold on. Right there where you have 1/2. Oh, never mind. You added it. Never mind.
Okay, so 600 over 30 should be exactly 20. So I think it's just when this got rounded because that's 0.0333 repeating, right?
Yes.
Okay, yeah, so it is 20. The math checks out exactly if we keep it as 1/30th, because then that's 600 over 30. That's revolutions per minute. So 600 over 30 revolutions, which is 20 revolutions. Okay, and if we check over here, yep, looks good to me. So does that clear it up, Deja, or do you still have some questions about it?
Yes, I get it now. I guess because when I started trying to use the kinematic equations, I did not convert the seconds to minutes.
Yeah, so as usual in the actual exam, I do try to avoid having you have to do unit conversions, but on the practice exam, sometimes I don't go through and do the conversions because it's still good practice in general to be able to do the unit conversions.
Another question that had me a little confused is question 2.
2. What is the angular speed in radians per second of the second hand of a watch? Okay, so angular speed is, at least on average, it's the angular displacement over the time it takes. But if the angular speed is constant, that's also what the instantaneous angular speed is. That's how fast it's going at any given moment. So we just need to figure out this time it takes for it to travel through a certain angle. What do you think is the most convenient angle here?
Radians.
Well, radians is the unit, but as far as like, we could say, well, how long does it take to rotate through pi radians, which is half of a complete circle? We could say how long it takes to rotate through pi over 6 radians, and we can figure all that out. But what's probably the easiest angle to look at here if we're talking about a watch? 2 pi. That's one complete rotation around because we know exactly how long it takes for a second hand to go once around on a watch. How long does it take? One minute, 60 seconds, right? So we're looking at this second hand. A little bit better. It's going around after exactly 1 minute, at least if it's working the way it should be, it's going to complete an angular displacement of 2 pi radians. So omega is, it travels through 2 pi radians in 1 minute, but it wants it in radians per second. So 60 seconds. So we get whatever pi over 30 is in radians per second. Or in decimal. Pi over 30.
Is it B?
Let's see, 0.1, yeah. Yeah, so I get 0.1 as well, 0.1 radians per second. So B. And so jump over here. B. So yeah, with ones like these, since I can't have you try and find like an instantaneous angular velocity when it's changing, because that in most cases requires calculus. If it's asking you for the angular speed and it's not like a kinematics problem where it's kind of clear, it's giving you lots of different variables, it's just saying, well, this is probably a case where it's easy to know exactly how long it's completing a full rotation. And so how long does it take to move through 2 pi radians? So there was a similar example on, I think, the homework, where it's like you've got the Earth rotating and you've got a city near the equator. And the question is, what is the angular speed of the Earth or that city? Same thing. And so the same deal applies there. For a complete rotation of the Earth, that's 2 pi radians it's rotated through, but how long does that take? How long does it take the Earth to complete one full rotation?
360 days. Oh no, 12 hours.
1
20
day.
A day. So that's the day-night cycle, is it rotating through? And so it takes 24 hours to complete one full rotation for one revolution around the sun. So that then you're talking about the Earth moving around the sun, not around its own axis. That's the 365 days, a year. So in a case like this, it would be 2 pi over 1 day. And if it wanted it in units other than days, you can convert days to seconds, that sort of thing. Okay. Does that clear that one up, Deja?
Yes.
Okay, good. I guess I drew this clock going the wrong direction, but it acts for the angular speed, so we didn't need the negative for that direction, but I'll still, for the sake of correctness, draw it going clockwise, which would be a negative rotation. Okay, other practice problems or questions?
For number 11, I had did it and I got the like I had found the acceleration first and I had stopped there and I got 14.92, but then I saw it was a tangent. I can't even say that word, tangential acceleration. So when you find the tangential acceleration, do you have to find the acceleration first and then put that into the tangential acceleration equation? I don't know if you're understanding what I'm saying.
Yeah, you did it exactly right, if I'm understanding you right. So this equation tells us tangential, but you can find this part through kinematics.
Yes.
Yes, that's right.
Okay. Yeah, because I had stopped right there when I just found the acceleration, and then I went back and I saw that I got it wrong because I put 15 meters per second squared and then I had it wrong. So I was trying to find out what I did wrong and then I put it into the equation. So yeah.
Yeah, and so if you find alpha, so what should the units of alpha be?
Meters second squares, meters per second squared.
Careful.
Radians per second square.
Radians, right? Because this is a rotation. It's talking about an angle and the rate of change of the angular speed. So how much of an angle is covering in a given time is changing. So radians per second squared, or radians per second is the change in that speed. But if you multiply that by the radius, which typically has units of meters, at least in SI, you get out meters per second squared, because remember, radians is just a number at the end of the day. It's like multiplying by 1/2. It doesn't change the overall units. It's just a sort of label that we give that, so we know we're talking about rotational motion. Okay. Here's a question though. If you are told that this ball is rotating around at a constant angular speed, what is the tangential acceleration of a point on, or what is the tangential acceleration of that ball?
0.
0, because the angular speed is not changing. There is no angular acceleration, and so there is no tangential acceleration. A point on, in this case, I guess we're talking about the ball going around a circle. If the angular speed is constant, then there is no change in how much its tangential velocity here versus here, at least as far as the magnitude. And that's what the tangential acceleration tells us, is that they changed from here to here. It's going faster. But if the angular speed is constant, then it's not moving any faster. It doesn't have any greater tangential speed over here versus prior. So don't let something like that trip you up. Okay, other practice problems we want to look at? And they don't have to be from this, it can be from whatever resource, just if it's homework, I don't have it in front of me, so you may have to read off the problem. Although I'm not gonna answer the homework questions that are due tonight.
I have a conceptual question, practice, chapter 9.
Okay,
The first question. So
Mhm.
it's saying, the drawing shows an overhead view of a horizontal bar that is free to rotate about an axis perpendicular to the page. Two forces act on the bar, and they have the same magnitude. However, one force is perpendicular to the bar and the other makes an angle theta with respect to it. The angle can be 19 degrees, 45 degrees, or 0. Rank the values of the theta according to the magnitude of the net torque. The sum of the torques that the two forces produce largest net torque first.
where is the axis for this bar? Is it on one end? Is it in the middle?
In the middle.
Okay. And then we're given one of the forces. It acts perpendicular to the bar. Is it acting at one end?
Yeah.
Okay. And then I'm guessing on the other end, you could have something acting 90, something like this. Or what's the third option?
So they gave us two. One is perpendicular, and the other one is like it has a theta, and we have to figure that theta.
We have to figure it out.
They gave us like they said the angle can be 19 degrees, 45, or 0.
Okay. So have I drawn it right? If I draw my third one like this, it could be any of those three choices.
So it's not the one that's perpendicular, it's the second one, the one that you draw theta.
Right, but is it, so 0 degrees would be, I assume this way, pointing towards the axis. And then somewhere in between, we'll call that theta, and then 90 would be perpendicular going that way. Is that the idea?
I'm not sure actually.
Okay.
Should I read the question again?
What number is it? So I can see.
Question 1.
Okay, question 1. So I'm pulling it up here on my phone. Fine. It's making me sign in. So 1 second. So I just want to make sure I have the picture right here. Okay. So yeah. Okay, so yeah, it's saying that you have, but yeah, I have to redraw that. It's saying between having a force acting at some angle like this, which I guess it calls phi in this picture. Versus 0 degrees, which means it's acting towards the axis. Oops. Versus 90, so it's acting perpendicular. If that force has the same magnitude as this one that we're given over here, whereas,
So I can't
Yeah.
see your screen.
what's that?
I can't see your screen.
Oh,
Can't.
let's stop sharing. Where did you go? Trying to minimize. Okay, how about now?
Yeah, sorry.
Okay. So it's asking of these 3 possible choices for the force over on this side, which one in combination with this force over on the right is going to produce the greatest net torque. So it may seem like it's going to be the 90-degree force. Wait. Yeah, length of line is a few according to magnitudes. Largest net torque. Oh, it's because I was gonna say that's backwards. I've drawn this one the wrong way. There we go. Okay, so it may seem like this 90-degree one is the most compared to, or is going to produce the most torque. But if this force is exactly the same as this one in magnitude, what can we say about the net torque those 2 forces produce together?
0.
0.
Or
It's this one's trying to make it rotate clockwise, while this one's trying to make it rotate counterclockwise. If they're both producing the same torque, which they are because they have the same magnitude and are acting through the same lever arm, then they're just going to cancel each other out to give a net torque of 0. And if we want to be specific about it, it would be that the one on the left produces a clockwise torque, so negative FL, plus the one on the right produces a counterclockwise torque, which is a positive FL, that equals 0. Okay, so that's one of these down. I'm going to jump to the 0-degree one. It's the one that's facing towards the axis, because that's going to tell us something about the one in between those 2 extremes. That's an argument that physicists like to use a lot, is look at extreme cases, and then whatever's between those 2 has to fall between them as far as the answer you get. So what is the net torque around this axis going through the center in the case where the force on the left is pointing towards the axis of rotation?
Counterclockwise.
Yep, it's purely this counterclockwise torque produced by the force on the right, because the force on the left has 0 lever arm. It acts through the axis of rotation. So our calculation here would be a clockwise torque times 0 lever arm plus that same counterclockwise torque, not 0, would be FL. Okay, so this is the 90-degree case. This is the 0-degree case. So the 45 is a little bit tougher just because we have to do our lever arm calculation. But what I was getting at with doing the 2 extreme cases is that if it's as small as it could possibly be, 0 net torque, when it's 90 degrees, and as large as it could possibly be when it's 0 degrees, because it's facing in towards the axis of rotation. Where does the 45-degree case fall?
somewhere in between, probably like 1/2 FL.
Yeah, it's somewhere right in the middle. So we don't even have to calculate it in order to be able to rank it compared to the other two. Conceptually, it may be easier to think about it as, so we know that if there's the 90-degree one, they're both trying to produce torques in opposite directions that results in zero net torque. Whereas with the 0-degree, we've only got the force on the right producing a torque, and so it's not being resisted by anything acting in the opposite direction. For the 45-degree case, we have this small component of the overall force, and that's what's resisting the counterclockwise torque produced on the right. So you've got less of a clockwise torque to try and balance out this counterclockwise torque. And that results in a net torque that is larger than zero because the clockwise torque can't completely balance the counterclockwise one. But it's also not all counterclockwise torque because the counterclockwise torque is being balanced by something over on the left. Okay, so the ranking should go from greatest to least net torque, 0 degrees, 45 degrees, 90 degrees. Does that clear that up, Ilham?
Yeah.
Okay. And if we wanted to calculate that torque produced, we can, because this is 45 degrees. So our F here is going to help if we draw this off to the side. F, we got 45 degrees. We got this right triangle. And so we want to find this side. So in this case, it's that F is adjacent to that side. So we've got tangent of, oh, I'm sorry. I'm finding it in terms of the force. We do it in terms of the lever arm here. So we want to do, that's L. And we want to find this side, which is our lever arm for the 45-degree case. So call that L2. In that case, it's that the sine of 45 degrees is L2 over L. And so L2 is L sine 45. And so our net torque is negative F times L sine 45, which sine 45 is square root 2 over 2, I believe. So plus FL. And that's going to give us something that is, we factor out, it's 1 minus sine 45. So I think that's about 0.3 or something time. Sorry, this should not be a equals. That's, we factored out the FL. So it's like 0.3 of the largest possible. Now, that doesn't really, it's not the best way about it to actually calculate it, but that's just to show you can if you want to compare it that way instead of the conceptual approach. Okay, any other questions on that bit or other practice exam stuff?
Can you please do question 5, still in the practice?
Question to,
No, I mean the practice, like the concept practice.
oh, okay. So it is loading. Okay, so this has a few parts to it. Is there one in particular?
Like I didn't understand like the force, like the forces, how how like the middle force and the forces on the edge.
So are you talking about the one where you have the three squares?
What do you mean? Question 5.
Okay. Does that look,
Yeah,
yeah,
like I understand how like the forces on the edge affect the force on the middle.
we're asked to rank or determine where the translational acceleration is 0, but angular is not. Translational is not 0, but angular is, and then both are 0. So I'll draw these in. This force F, and then 2F, 2F, and 2F, and F. So we're asked about when translational and angular accelerations are 0 and are not 0. What is required for a translational acceleration to be 0? Or what does that imply, I guess?
Is when the angular speed it's constant.
So translational acceleration along a straight line. When is that 0?
When the tangential velocity is 0, it's constant.
Is constant, yeah.
Acceleration is at equilibrium.
It's at equilibrium. And equilibrium tells us or implies that the net force acting on the thing is 0. So that's the corresponding thing for the translational acceleration being 0. Angular being 0 is because the net torque is 0. There's nothing to change the rate of rotation. Just like for this up here, there's nothing to change the rate of linear motion. So it's asking us, when is the net force 0 and when is the net torque 0 for each of these cases? So let's start with this one. What is the net force acting on this block? They're all acting along the y direction, so we only need to worry about the y forces. But what are those going to be? Yep, 4F, because it's F plus 2F. F is 4F. So is that thing, does it have a 0 translational acceleration?
No.
No. So A, we want to be specific, the y component, but that is the only component here, is not equal to 0 meters per second squared. What about the torque? Where the axis in this case is through the center of the block. It's a square, so these two pieces are equal, whatever they are, call them D. What is the net torque acting on this block?
Is it also 0?
So, well, also, or, because right, the acceleration.
Oh, I was looking, yeah.
Yeah.
Okay.
But, okay, I agree with you. Do others see why the net torque should be 0 in this case?
Is it because the force and the lever arm on one side cancels the one on the other side?
Yep, you've got a clockwise torque produced by this force on the left and a counterclockwise produced by the force on the right. How much torque does this 2F force produce?
0.
None, because it's going through the axis. Okay, so without even really calculating anything, we can see that the net torque is 0. But if we want to, again, we can say the counterclockwise torque is positive. So F times its lever arm, which is D, because that line is perpendicular to the line of action of the force on the right. And then same with that on the left. So FD minus, we've got a clockwise torque, the one on the left, and then plus 2F times 0. So since it doesn't produce a torque, whether I call this plus or minus, doesn't really make a difference. It doesn't produce a clockwise or counterclockwise torque. So really it's the fact that these two cancel each other out. So we do get 0 torque. And so angular acceleration is 0 radians per second squared. Okay, so in this case, we do have a translational acceleration, but don't have an angular acceleration, or it's equal to 0. What about this second case? So call this case A, B, C. This was for A. Now looking at B. What is the net force on that block?
Zero.
Yep, F plus F minus 2F, that's 0. So translational acceleration is 0. What about the net torque? Do you see that it's no different from case A?
Yeah, it's 0.
Yeah, because in this case, we've got two forces producing torques that balance each other. And then we've got this force that acts through the axis, so it doesn't produce any torque. The net torque is 0. Angular acceleration is 0 radians per second squared. That one has neither linear or angular acceleration. And then case C, what is the net force in that case? One still there? Oh, case C, what is the net force acting on the block in this last case?
Is it 0?
It is 0 because we got 2F acting upward minus F. That's 0 newtons. And so the acceleration is 0 meters per second squared. It is not accelerating linearly. But then what is the net torque in this case?
Is it clockwise?
It is clockwise. So we have a non-zero net torque because these two will balance each other because they have equal lever arms, but act in opposite directions. The one on the left acts counterclockwise, the one on the right acts clockwise. But then we've got this one up top, and it's not balanced by anything. So we see immediately that we do have a non-zero net torque, but if we want to calculate it, we can say we have a clockwise net torque on the right, or we'll start with counterclockwise. Counterclockwise net torque on the left, FD, minus that one on the right. And then we've got a clockwise torque up top, so that's negative 2F, also times that distance, whatever that distance is. And so these two balance each other, but we're left with a net torque of negative 2FD. And the negative, all it's telling us is that it is a net clockwise torque. So angular acceleration doesn't really look like an alpha, but angular acceleration does not equal 0 radians per second squared. So with the same forces acting, but acting in different locations on the object, we can get either no linear acceleration. Well, in this case, linear acceleration, but no angular acceleration. We can get no linear acceleration or angular acceleration, or we can get linear acceleration, no linear acceleration, and then angular acceleration.
Is it possible one of, like, for example, 2F force to do a counterclockwise
Mhm.
torque?
So that would be if we had something very similar to that last case, but instead that 2F acts to the right of the axis of rotation. Because then it would produce a counterclockwise torque. The net torque in that case would be a positive 2FD, whatever that distance d is. Okay, does that clear that one up?
Yeah.
So if I were looking at this problem in my head, I would probably not be doing all of the calculations. I would just say this force, the torque it produces balances this one. This acts through the, y'all are seeing my cursor, right?
Yeah, we can see.
So yeah, the torque produced by this force is balanced by the torque produced by this one. This one acts through the axis, so net torque is 0. Move on to this one. These torques, left and right, balance. This one still acts through the axis, net torque is 0. These balance. This one is not balanced by anything, does not act through the axis. The net torque is non-zero. And then the forces hopefully are pretty quick. So if I were doing it in my head, it would be more of a conceptual problem, but to go through it step by step and explain it, it sort of becomes a calculation problem, if that makes sense. Okay, other practice questions?
I was confused about question 8.
On the practice exam or still the practice?
Yeah, still the practice.
Okay.
So what it's asking where the center of gravity, where is it located? So at the first I was thinking it was located like in the middle of the bottle, but it was wrong.
Okay. So let's see. So we got wine bottle. And the question is where its center of gravity is. So when did we say that objects balance?
When the center of gravity is in the center of the object.
Not necessarily when it's in the center of the object, but when it's the
Oh,
object
when
supported at the center of gravity.
when the torque is done by the weight.
So here, I'm going to go back to the notes real quick to talk about this. So where is it? Okay, this part. So yes, center of gravity is the point. We can treat the weight of an object as acting when we're considering the torque that that weight produces around an axis. Okay. But if all the only force acting on the object is the force due to gravity, then it's only going to produce a torque when that center of gravity does not agree with the axis of rotation. Okay, so the reason this object balances here at the bottom is because the weight of the object can be treated as acting through the center of gravity. And so if you're supporting the object at the center of gravity, then that weight is not producing any torque around that rotational axis. And so if it's not producing any torque, this board can't rotate clockwise or counterclockwise, meaning it balances. So over here, very similar idea of if this system is supported at its center of gravity, it won't produce any torque around that point because the center of gravity is the axis of rotation. Here, our axis of rotation would be right there. So the only way this bottle isn't going to tip left or right is if the center of gravity falls somewhere along this line. Because if it were to the right, like that, it would produce a clockwise torque. The bottle would tip over that way. If it were over here, then the bottle would tip over that way. If it's right here, right above the support point, which is the axis of rotation, then it's not producing any torque around that point. And so the object doesn't rotate one way or another, meaning it balances. And so that's why the answer is, how does it word it? Yeah, directly above the point where the wine rack touches the tabletop. Because in that case, the net force is 0 because you're applying a force to balance out the entire weight of this system, but also the net torque is 0 because the weight of the object does not produce any torque around that point.
Can you give me please another question like this where I can figure?
Okay, let's see. So when we stand, our center of gravity, we're just kind of standing in this neutral position and are not broken into pieces like this guy turned out. Let me try that again. Standing in a neutral position, our center of gravity sits somewhere between our feet. And so the net torque produced around this sort of axis of our 2 feet is 0 because the center of gravity sits right between them. We can think of it as the normal force on both feet is equal. And so in that case, they produce equal torques around that point. And so we don't fall over because our center of gravity falls right in between them. But if we maybe bend over something like this, our center of gravity shifts a little bit to the right. And depending on how our arms hang, it may not even be within our actual body. It may be kind of somewhere in the middle because that's the average position of the weight of your body. So in that case, how you're kind of supporting yourself, the axis of rotation here is your feet. And so if you have this center of gravity to the right of your feet, you end up producing a torque around that axis, you fall over. So the whole reason that we can like touch our toes, that sort of thing, is that we make a point of keeping our center of gravity above our feet so that we don't produce a torque around the axis consisting of our feet. How help?
Yeah.
Okay. So that one is more difficult, but the idea is that things balance when you have the center of gravity lying along the same line as the pivot point where the thing would want to rotate typically. So for the board here, it would, if we did have a net torque, tend to rotate around the point where it's sitting on the ground. So you want to make sure the center of gravity sits somewhere along the line above it so it doesn't produce a torque. Same here with leaning over. Our feet are the axis of rotation where we would tend to tip over one way or another. As long as we keep our center of gravity over our feet, which we could do by just not leaning over as much, then we don't tip over because we don't produce a torque around our feet. Okay. Other questions?
Question 11.
Okay. Is loading. Rods are free to rotate. So draw it first, and then we'll go through it. Axis is over here. Let's see.
Sorry.
Mhm.
That on question 11 we have a triangle. I think that's question 12.
Oh, it's a two-parter. So the triangle is the second part.
Yeah. So it's question 11.
Okay, so not that one.
Yeah.
All right,
Sorry.
that's all right. Uniform material. For which axis is the greatest net extent of torque required to bring the triangle up in angular speed? Oh, there's a little bit of a doozy. So got A, B, and C. And it says this sheet is made of uniform material. That is important here. Three possible axes of rotation, A, B, or C. Which axis requires the greatest net external torque to bring the triangle up to an angular speed of 10 radians per second in 10 seconds starting from this. The numbers don't really matter there. It's just saying if you have the same net torque, and the yeah, if you have the same net torque, but put the axes in three different places, I'm going to try and represent it like this, being into the page, sort of. So those are the three possible axes. Since the net torque on something determines its angular acceleration through this factor, the moment of inertia, angular acceleration is net torque over that moment of inertia. And so we're essentially being asked, in which case do we have the largest moment of inertia? Because the larger the moment of inertia, the smaller the angular acceleration. And so we're asked to rank it in terms of, oh, greatest net external torque required. Okay. So the larger the larger the moment of inertia, the more net torque we need to get out the same angular acceleration. And so we have to figure out around which axis is this object going to have the largest moment of inertia. So what is moment of inertia again? Just in its conceptual sense.
Is when the object don't want to rotate.
Yeah, and what makes it harder for an object to rotate? What makes it have less of a tendency to?
When it has a lot of mass.
If it has a lot of mass, that's one thing, or if the mass is,
I don't know.
if the mass is distributed farther from the axis of rotation. Right, remember the disk versus the hoop. So disk, we've got mass distributed throughout this whole thing. Hoop, we've got it distributed around the edge. If we're trying to rotate through this axis passing through the center of each, which is going to be easier to rotate? If they both have the same mass, at least.
Is it the hoop?
So no, because we've got more of the mass is concentrated away from the axis. Right, so moment of inertia depends on mass distribution even more than it depends on mass itself. So with the disk, solid disk, you don't have mass just sitting as far away from the axis of rotation as possible. Instead, you've got some a little bit closer, some a little bit farther away, but that's better. It produces a lower overall moment of inertia than if you have all the mass just sitting all the way out away from the axis of rotation. Okay. The farther mass sits from the axis of rotation, the more rotational inertia the object has. And so, which of these axes, A, B, or C, is going to put the mass overall of the object farthest away from the axis of rotation?
Is it the axis of rotation? Is it in the center of the triangle?
Well, it's asking if we make the axis of rotation A, B, or C. So if we have that triangle rotate about one of those three axes, which one is going to result in the triangle having the greatest moment of inertia about that axis?
Is it B?
The answer is B. Do you see why it's B?
Yeah, I think because it's too far.
Well, yeah, so if we kind of look at this triangle and say, well, it's uniform, I think the average position of the mass, right, where it roughly averages out to, somewhere maybe right there, right? That would be considered the center of mass of the object. So, but what that is really saying is that the mass is more concentrated over on this side than it is over here, which I think you can see, right? We've got this thinner slice of the triangle over here. So it makes sense that the mass is more in this bulky part.
Yeah.
So if we have the axis of rotation at B, that puts this kind of concentration of mass farther away from it, and so increases that moment of inertia. And like we said, the larger the moment of inertia, the more net torque we need to get the same angular acceleration.
Yeah.
That is like I said when I first looked at it, that one's a little bit of a doozy in that it takes a lot of steps, and it's, you know, you don't have an equation for this, for the triangle. That makes it tougher to think about it. But the idea at the end of the day is moment of inertia is largest when mass is farthest away from the axis of rotation. And that's why, even without knowing the equation, if I have a rod rotating around its end versus rotating around its center, which one has the larger moment of inertia?
The first one?
The first one, because here, the farthest away that any of the mass gets is L/2 on either side. But for the first case, it can be as far as the whole length of the rod away. So this little bit of mass at the end of the rod has a very large moment of inertia compared to this bit right here. And we have kind of that same situation going on along the entire rod. Here, it's not as far away, so it doesn't have as large of a moment of inertia as that little bit right there, and that adds up to where the overall rod has a lower moment of inertia for this axis than the first one.
So do you think I have to like understand each question in the concept and the practice question?
I wouldn't say all of them. I mean, it's 40 questions, so that's a lot. But I think if you understand, I can't really give a percentage.
Like, how can I know like this is important or not?
So it looks like a lot of these are multi-part questions. It's typically, if you can answer the first one of the multi-parts, then I think you understand it well enough. So that one that I started doing, which was the first part of that problem, if you understand how to answer that, I think you understand moment of inertia well enough. This is sort of a stretch in comparison, but it's all the second question. Yeah, and then the last one is like the who can lean forward farther, whose center of gravity sits lower. That's like what we talked about up here, but that is a more difficult conceptual example. So usually it seems like they put the easiest one first if it's a multi-part problem. If you can do those, I think you're okay.
Okay.
Other questions?
I think everyone is gone.
Oh,
Yeah.
yep, looks like it. Okay, well, do you have any other questions?
I'm just looking at the practices, just seeing what's the difficult thing.
Alrighty.
So in question 23, why like the both masses? It should be equal, but it's saying mass one is more, it has more mass than second.
Okay, it is loading.
If you think that this question, like, it's not important to know, so we don't have to like waste time doing it.
I think this one, there may not be anything specifically like this with this pulley, but I think it is a good question. I guess I'll put it that way.
So do you think I have to know how to do it?
I think it is something that you should understand because it's very similar, if not the same as, you've got a mass on two pieces of a board, you've got an axle or a fulcrum somewhere between. You want to know how these two masses should compare if this system is in equilibrium. That is pretty much identical to this problem because all we're looking at instead is you've got something pulling there, something pulling there. The axis of rotation is there. Doesn't that look a lot like this problem up here? If that right there is your quote unquote fulcrum.
So based on what you've said earlier, so I think the one that's further from the rotation axis will be massive than the one it's nearer to the axis of rotation, right?
Well, so we want this system to be in equilibrium. What does that require?
So in this case, I think mass 1 should be greater than mass 2.
Well, no, so mass 2 should be greater than mass 1.
Yeah, never mind.
So the reason why, compare this to this problem up here. You've got a fulcrum, you've got a mass right here, you've got a mass right here. How should those compare in order to make this board balance?
Okay, so the one that's very near to the center should be massive.
Should be more massive, so it can produce a larger, well, not a larger overall torque. It has a short,
Balance.
yeah, it has a
Yeah.
short lever arm. And so to produce the same torque as this one produces, it has to have a larger mass. So
Yeah.
it's larger weight.
Mhm.
Yeah, so this one with the pulleys is essentially identical to that.
Mhm. Okay.
Yeah, so we never did much with pulleys, but it's like, if you understand why M2 should be larger than M1 for this, then you do for this, which is a more relevant problem.
Okay.
All right, any others?
So when, like generally, when they say about rigid body,
Mm-hmm.
they're like specific thing to think about rigid bodies or?
Rigid body just means that everything moves together. It's not like Jello. Like if you apply a force to one part, it sort of takes the rest a little bit to catch up, and that force is not sort of evenly distributed across the surface. Because if you've got something like that spinning, it can actually sort of shrink or stretch as it spins. And that's a lot harder to analyze. So rigid body is just, think of like a solid block. All the points on it stay a fixed distance away from each other because it never stretches or compresses. So we are never not dealing with rigid bodies, I guess I'll say, in this class.
Okay.
Yeah, everything you're looking at is by default a rigid body because non-rigid bodies are very complicated. Except for, I guess, springs themselves are not technically rigid bodies, but we're not worried too much about that for spring. We're just worried about the spring constant is the big thing there in Hooke's law. So yes.
Okay. Generally, do you think exam 3 is harder compared to the others?
I think it depends on you. I personally think it's probably the easiest one, but that's because it's behind me. I know this stuff now.
know.
So
I feel
looking-
like most thing that trips me off is the concepts questions.
So you might notice when I do the quizzes,
Mhm.
a lot of the way that I end up saying why certain questions are wrong when I do the solutions is I say that did happen. What is a consequence of that that doesn't make sense? right? So
Mhm.
that's called a proof by contradiction. You say, well, okay, pretend that is the right answer. Well, that then means that so-and-so also has to be true, but I know that's not true. So therefore the original thing cannot be true. I think that's a good way to approach concepts when you can't immediately narrow in on the right answer, is just be able to show why all the other answers are wrong. And then all that's left is the right answer.
So I think if I do the practice, I will be good on the concept.
I think so.
Okay.
Yeah. And of course, the practice exam too has some conceptual questions.
Yeah. Okay.
And
Well,
the quizzes.
Yeah. The quizzes. Yeah. Well, the quizzes it's from the practice questions.
Yeah, but they do also have the like detailed
They-
solutions, right, that I wrote up. So I will post the chapter 10 quiz solutions probably later tonight. It's just I had some people who still needed to take it today, so I couldn't post it yet.
Okay.
Yeah.
I think that's it.
All right, well, I'll have this posted once it renders. I'll have it posted up on YouTube, so it should be easier to get through than when I had first posted the last one.
Yeah. Well, that's it. I feel like I had a lot of questions, but it's not popping right now.
Okay, well, you can always email if you have any others.
Yeah, I'll definitely do that.
All right.
Thank you so much.
Mhm. All right, enjoy your weekend.
You too.
Thanks.